This video focuses on inferential statistics. Remember from the last video that inferential statistics are helpful for assessing the likelihood that the observed results can be generalized to the population. But it's also useful for estimating the significance of a difference or an association and controlling for the chance that observations are wrong due to random error inherent in the sample. Remember that systematic errors are controlled for through attention to threats and internal and external validity, and that happens in the design phase. Let's talk about error in a little bit more detail. Whenever we draw a conclusion about whether a difference or an association exists using inferential statistics, 4 distinct possibilities actually exist. If we talk about a hypothetical difference between groups, you could be correct in saying that a difference exists when it really does, or you could be correct in saying a difference doesn't exist when it really doesn't. But there are 2 ways you can be wrong as well. You could conclude that a difference exists when in reality it doesn't. This is considered a type 1 or an alpha error. Or you can conclude that a difference doesn't exist when in reality it does. This is called a type 2 or a beta error. So what are the consequences of being wrong? In the case of an alpha or type 1 error, this might result in people being given ineffective treatments, which is more problematic if the treatment has harm associated with it, for example, chemotherapy. So how are we ever sure that we haven't made this error? Well, you can't be 100% sure. There's always a chance for error. But typically we set the required alpha level to 0.05 to determine if something is statistically significant. This is your p-value. If you boil that down, what that really means is that 95 times out of 100 we will correctly conclude that the difference exists, but 5 times out of 100 we will commit a type 1 error. If we wanted to be extra conservative, we could change the value of the alpha and set it to 0.01. In this case, we would only accept 1 time out of 100 where we would commit a type 1 error. In the case of a beta or type 2 error, the consequence is that a potentially beneficial treatment would not be given based on the results of a study with a type 2 error. Basically, you're falsely accepting the null hypothesis and you wouldn't give the treatment even though in reality it's beneficial. The chance of making a beta error can be reduced by increasing the study power. Power is equal to 1 minus beta, and power is typically set at 80%. There are multiple ways that we can ensure a study has maximized its power to detect an effect, including maximizing the potency of the independent variable, which is where you increase either the frequency or the intensity of the intervention and to increase the size of the effect between the pre and post-test scores. In this case, if you thought a little bit of exercise might be useful, maybe we're going to give extra exercise in order to make that really potent and make sure that we see an effect. You can also minimize the noise or the variability by making comparison groups more homogeneous, so making groups more similar in all the characteristics that might affect the results, or by using a more reliable measure, so making sure that we're reducing the amount of measurement error that exists, or by ensuring that we have good rater reliability, in which case you want to make sure that the raters are tested for their reliability and that they're potentially trained to make the most reliable measurements they can. And finally, you can increase the sample size to make it more likely that a difference or an association will be statistically significant if it's truly there. Okay, now that we know a bit more about error associated with inferential statistics, let's actually delve deeper into how we can know which one to use. There are generally 5 criteria involved in selecting an appropriate test, and you can use them to evaluate whether or not the correct inferential analysis was conducted in a study that you're reviewing. First, you need to decide whether the hypothesis is testing a difference or an association, and the wording of the hypothesis will help you understand this. Remember that a difference equals a difference in outcome between 2 distinct groups or in repeated measures of the same group. And an association is a relationship or an association between measurements on the same group of individuals. Second, you need to look at what level of measurement the outcome data can be classified as. So look to your dependent variable to help you make this choice between nominal, ordinal, interval, or ratio level data. Third, the number of comparisons should be looked at. So for difference questions, this means the number of groups or the number of comparisons that are made between groups. For an association question, this really means the number of independent variables that are being studied in relation to the dependent variable. A side note here, when you have multiple groups, you will have many comparisons, and multiple comparisons increases the chance of creating or making a type 1 error. For example, if the overall alpha level of the study is set to 0.05, which is typical, and we have 4 groups to assess differences between, then you're actually making 6 different comparisons separately. So the real alpha level is actually 0.05 times 6, or 0.30. So 30% chance of making a type 1 error. It's unacceptable. So there are multiple solutions to deal with the problem of multiple comparisons. You can apply a correction factor, the most common of which is called a Bonferroni's correction, which is where the alpha level is divided by the number of comparisons. So the 0.05 gets divided by 6, and we get a new overall study alpha level of 0.008. And so every individual comparison is then compared to that alpha level in order to be determined whether it's statistically significant or not. The other technique is to use something called an overall analysis, and this will actually be done to find out whether or not a statistical significance has been obtained in the whole study. So all groups, all variables, all comparisons. Is there something significant there? But the problem with that is it only tells you that a difference or an association exists, but not which one of those comparisons actually has the difference or the association that's significant. And so what you need to do is you need to follow up with post hoc tests to identify where those differences exist. Okay, back to our criteria. The fourth criteria to determine is whether the sample was matched or unmatched. So keep in mind that people are very heterogeneous, and they're difficult to match people with other people. Typically, if we're going to match people, you'll see that the groups will be matched with someone. So a person in one group will be matched with another person in the other group, and they might be matched on age or sex. And that helps control for those variables that they're matched on so that they don't have to be considered in the analyses. But we can easily do this in stratified sampling as well. So the most conservative approach to matching is to have patients serve as their own control, or in a repeated measures design where the same people are measured on multiple occasions. Finally, the fifth criteria is to examine the sample size. Generally, studies with greater than 30 subjects are considered large enough for most statistical approaches. And there are some very specialized tests that need to be used with very small sample sizes. The golden rule is that there should be at least 5 subjects in any kind of cell or subgroup in order to actually use the typical statistics. Otherwise, you need to use these special statistical approaches and to control for the fact that you don't have good enough sample size. We'll use a general flow chart to show you in class how you can assess whether studies have used the right statistic. The validity of the conclusions drawn from a study requires appropriate application of statistics. So you should always ask these questions to any study you're appraising. Have all the questions or hypotheses posed at the outset been analyzed? Or did they provide an answer to everything they asked? Did they use both descriptive and inferential statistics? They first have to describe the sample to you and then decide whether or not they're generalizing beyond that. Was the correct statistical test used based on those 5 criteria? And have the assumptions of the statistical test been violated in any way? This is, if we think about that, is going back to maybe that small sample size component, but most of evaluating whether the assumptions have been violated is well beyond the scope of this course, and probably actually beyond most people other than statisticians. And then finally, you have to think about the statistical significance and the clinical significance of the outcomes to your practice. So if the results are statistically significant, are they clinically relevant, which is the most important thing for you to decide? Because clinical relevance doesn't necessarily come directly from statistical significance. And finally, if the results are non-significant, could it be due to low power? Right? Is there a chance for them to have created a type 2 error?